Yep. So can you see my screen?
Yes, sir.
Right. Yeah. So a quick recap of the last session. So we are covering about the game playing search or the adversarial search. The first strategy was the backtracking, the normal backtracking search. So using the backtracking search, we can decide what is the optimal move. So see the question here. So at the bottom, the question is here. How do we search this tree to find the optimal move? So for example, this is the root node tic-tac-toe problem. There are 9 possible moves. Move 1, move 2, move 3, move 4, and so on and so forth, move up to move 9. So out of these 9 moves, which one is the best move or the optimal move? So how can we do this using the backtracking search? So we can come down up to the leaf and see the value, propagate it back. So in every segment, we should propagate the utility value, the result. So we have to see the result first from the leaf and get it back. Then get the information back to the root node and then decide which one we should explore. Because this propagation is little bit different than the previous conventional backtracking search. The only difference is at every stage, you don't have to, I mean, we don't have to think with our brain. We have to go into the brain of the opponent also. So every time, this is the move for the mean. Which one should mean pick? This is the move of max. Which one max should pick? Then this is mean. What is the best move for mean? So this way we have to think that way. So once we get the result, and then we back propagate up to the root node. So we should think in that way during the propagation, and that is basically the backtracking search. And then we learn there is a better strategy to do is the minimax algorithm. So what is the minimax algorithm? Uh, so well, actually, this is the minimax algorithm. Sorry. So just that actually minimax is the same as the backtracking search, just in two different platform. I mean, with respect to max and with respect to mean, the backtracking search is called the minimax algorithm. Very simple. The algorithm is also written somewhere here. Uh, I'm not sure somewhere. Uh, yeah, but anyway, I mean, maybe somewhere. Okay, I'll check it later. So again, uh, uh, so the backtracking with mean and max, we are calling it the minimax algorithm. Well, the next better strategy is minimax, but with heuristics. So what is that? We don't need to go till the leaf. I mean, we don't need to search the whole search tree, the whole search tree. What we can do? We can come up to certain levels, say maybe up to two move. Move one, move two. I mean, two level. And then you don't need to explore these things at the very first stage. So calculate the heuristic value. So heuristic of this one, heuristic of this one, heuristic of this one, and all the heuristics of this one, and then see. So heuristics with respect to what? With respect to max, because we are playing on behalf of max, and see the best heuristics, best value according to the heuristics, which is the best for max, and get it back this way. But again, up to this two level, we have to think in the context of mean and max. So because this is the from here, once we get back, we should think in the mind of mean. What mean should pick based on the heuristic value? What the mean should pick, and then based on the mean pick, what the max should pick, and then you decide. And once you decide, say for example, we decide this part, then the automatically we know what the mean will pick after that move. So maybe say this one is the first iteration is done, and then from here we will again go up to the level 2, another second depth, another two more depth, and this way we will actually continue. And exactly this is what we have covered in the first session of today's class. Exactly, you can see here, this is the starting move. There are three possible options because there is a symmetry. The 9 different moves has been clustered into three clusters. So This is level 1 and this is level 2. And now we are picking the heuristic value. We are calculating the heuristic value. And based on the heuristic value, you can see, so upon this, the best heuristic value for, so this is the mean, right? And this is the max. So the best heuristic value for mean is -1. So that is -1. Here, -2. That is -2. And here, 1. So that's why this is 1. And now the turn for max. So upon -1, -2, and 1, the best value for max is 1 because max want to maximize. And so we pick 1. Right. So once we are done, then 1 means what? 1 means this is actually max will pick. And immediately next mean will give the move the smaller value, and that is actually this one. So up to this is done. This is actually the first iteration. Okay, and now again here, right? Here is the turn for max, the next move for max. And max will do the same thing for the again another 2 level, and it will continue. And exactly it is given here also. You can see the next iteration for the max. And then the third iteration for max. And it will continue like this. That's it. This is what we have covered up to the in the last session. And then we were talking about, that was the tic-tac-toe problem. But what about the chess problem? So how we calculate the heuristic value? For the tic-tac-toe, we have covered in a different, the heuristic value was very problem specific, domain specific. And again, for the chess, this is also domain specific. This is not a very straightforward way. For example, in this problem, you can see this is one configuration or one state. This is another configuration. Here, all the black and the white in the left figure and also in the right figure are the same. So if you calculate the heuristic value according to the formula, that number of black component minus number of white component, then the heuristic value of this state and this state will be same because the similar number of components are here. Even those which are not available, I mean already out of the board, that is also same. So you cannot simply calculate number of white number minus number of black. No, that will not work. Rather, you have to take the position and the power. So what we can do, that is written here. See, so for every component, you have to think about the power because the power is also important. But again, if you think about the power of this state and this state is again same because the similar components are there. Remember, even though these are same, only one change is here. The rook is here, the bottommost rightmost corner, but here the rook is just in this position. You can see the difference of the rook. And because of this, if it is the white to move, then in this situation, white will lose the game, but here white will win the game just for the one single difference. So here what we can do to find out the heuristic value of these two different states. Remember, we have to distinguish between these two states. How we can do that? So we can do that by incorporating the position also. So for every single component, we can use multiple weight factor. So what is its weight? I mean, what is its power? So what is the power of the rook? And also, what is the position of the rook? So position means how many components it can attack at that position. So if you incorporate this idea into the heuristics, then you can see the difference between the two configuration, and definitely we will pick this one. So hope you understand. This is what is the takeaway message from this chessboard. Definitely, this is a very a big problem. Maybe you will not be asked to solve it in the exam hall, but might be partially you will be asked to just to share the idea what we should do or that, etc. Otherwise, definitely I will not ask you to solve the whole problem, but might be a small fragment of the problem that could be there. Okay, and then yeah, so this is what we have covered, the minimax algorithm, and this is the cutoff depth. So minimax and then the cutoff. Cutoff means up to level 2, and then again, let's say second move up to level 2, this one. But now another thing, the basically the last part, that is what I was expecting to cover in the last session, but I couldn't. So this is actually, we want to go one step further. Even in some problem, if you go up to the second move or the level two, that is even too much, too much. For example, 35 to the power 2. So level 1, so in every node there are 35 branches. For second node there are another 35, or even this could be even more than that. For the Go game, even that is too much for to explore up to level 2. So what we could do? Well, the next strategy is pruning. We will go up to level 2. That is fantastic. That is good. But we want to do one more improvisation, and that is pruning. You know what is pruning? We want to cut off some of the branch. Those are not necessary. And how we could do this? The name of the strategy is alpha beta pruning. Alpha beta. Previously it was minimax. This time this is alpha beta. Now let me clarify what is alpha beta pruning. But before, this alpha beta pruning basically use two strategies. One, this one. So think about it. If a position is bad or probably bad means based on the heuristics, you can see that this position is bad for me. Then is there any necessity to see how bad it is? You can say this state is bad because, say for example, from here there are two options, action 1 and action 2. So you can see action 2, say the action 2, the heuristic value for action 2 is good, better than the action 1. So in other way, say this is bad for me, then should I expend more time on exploring how bad it is? No, that's a very bad idea. Once we can see that the better idea, then we should dig into the deeper stage of the better alternative, better options, not for the bad options. So this way we can cut off the branch. So cut off the branch means all the nodes underneath of that branch should be cut off. In that way, we can save time. So this is strategy number 1 under the alpha beta pruning. And that's why you can see there is alpha and there is beta. So one is called alpha and other is called beta. I will explain one by one. So one idea is this, that if a position is probably bad, then don't go for exploring how bad it is. Okay, now the other one, the second one. If you can see there is it's a, well, again, say for example, there are two nodes, two actions, action 1 and action 2. And now you can see that the heuristic value of action 1 is better than the heuristic value of action 2. But you are confirmed, this is confirmed, that there is no way you can go for action 1 because the adversarial move, they will not allow you to take the good position. They will not allow you to take this move. So you have two options, action 1 and action 2. But even though the action 1 has better future, but the opponent will not allow you to take that goodness from with that move. So if that is the scenario, then why should we uh, spend time on finding how good it is? So that is another way by which we can prune the tree. So you can see it is no use expending the search time to find out the good positions. Remember the good positions that the adversary, means the opponent, won't let you achieve anyway. They will not allow you to take that goodness. So stop exploring further to find how good it is. Rather go for the bad options, because that is you are forced to do. There is no way you can. So stop exploring the good things that is already blocked by the adversary. Okay, excellent. Now already the idea is clear. Now let's straight jump into the example, and then it will be very easy for you. Okay, so again, the same examples that we have covered just a while ago. So you can see the examples here. Already the whole search tree is here. But remember, this time we'll not cover the whole search tree. We'll go step by step. So again, conventionally, we follow the backtracking because everywhere there is a backtracking, but we are doing some improvisation. Definitely, we'll go for the cutoff, and then we'll go for um, uh, the pruning also. So see, listen to me very carefully. This is very important. So this is called alpha beta pruning, and we have given an example. So see, so remember there is only two move. This is a very small example. Two move. First turn is for max, and the second turn is for mean. So max has to decide because max has multiple options. Which one max should pick? So with that intention, max start. So can you hear me?
Yes, sir.
Hello? Yeah, yeah, okay. So max start the move. So remember now the max has an infinite choice. I mean, max cannot decide the value. So that's why this is from minus infinite to plus infinite. I mean, max has not yet decided the heuristic value. Remember, it will come back once we explore the this part, and then it will go back, and then we'll decide what is the value of the for we in this branch. So this is undecided yet. That's why this is minus infinite to plus infinite. So okay, so let's move on to the next level, and then the turn for mean. And here again in the brain of mean, again mean this is undecided. Mean can take any value still because mean doesn't know yet. And now we come to this branch. And here, after coming, we can see the 3 here. You can see this will be 3. So immediately once we see the 3, 1, 2, and see the 3 value here, then mean will change its mind. So what should be the intention of the mean from this point? Who can answer? What mean should look for in order to I mean what is the intention for mean for the other children? With what expectation? Yeah, mean will look for less than is equal less than 3, right? Because already mean get 3 here. So the next two or whatever, the intention of mean is to it will try for some value less than 3 because already 3 is found because the target of mean is to minimization. Already get the value 3. Now definitely if something is bigger than 3 that will not be chosen by mean. So the target of mean is to find the lower than thing. So once this has been this is seen, then immediately the decision of mean will be less than. So that is what is shown. You can see here. And now it will go for it. So now every time you have to ask, should I explore this one according to mean? Is there any possibility to get a value less than 3? Yes, of course, there could have been 1. Why not? We should explore it. Because this is the turn for mean. Forget about the max. This is the turn for mean. So mean is looking for less than is equal to 3. So definitely there is a possibility that there could have 1 or 2. So definitely, or even minus value. So definitely mean will explore it. And once mean explore, it can see there is a 12 here. So once this is 12, it is of no use for mean because already mean has found the 3. So that's why this is of no use. So this goes it will go in vain anyway. Then it will look for this one again. Every time you have to think, is there any necessity to explore this one? Explore this one means this one and underneath. Remember this one and underneath. Yes, still there is a hope that the mean can get a value less than 3. With that hope, mean will found and ultimately it can see that this is 8. So already all 3 has been explored by mean. So mean decision has been final. There is no minus infinite to plus infinite or minus infinite to 3. The decision is done and that is 3. You can see the 3. The same thing. I mean, minimum to maximum value. I mean, the range is 3. Already is 3, exactly 3. So based on the decision of mean, max also changed its decision. because this is propagate upwards. Now the decision of max is, well, already in this branch, mean will allow me to take the value 3. So there is no way I can, so definitely I should look for the other branch with the hope of more than 3. So that's why max decision is going for less, greater than is equal to 3. So with that hope, well, yeah, so with that hope, now see the situation. With that hope, greater than 3, max come into this position, the similar way, come up to this position, and again, you can see the 2 is found here. So similarly, like this one, max mean again change its decision in this branch. It should be, you see, it should be, I mean, the new decision for the mean is less than is equal to 2. What does it mean by less than is equal to 2? Less than is equal to 2 means mean will look for the neighboring child, means the other child, with the hope of whether it can find the less than is equal to 2, any value less than is equal to 2. Now the question, here comes the question. See the beauty here. Is there any necessity to go for exploring this branch? No. Why? Because already there is a conflict. Because we are playing on behalf of Max. So Max has decided I will pick the value greater than is equal to 3. And now mean has decided I will take the value less than is equal to 2. So why should we go for further exploring? Is there any value exist that is greater than 3 but less than 2? No. There is no such value exist which is greater than is equal to 3 but less than is equal to 2. It's funny, right? I mean, there is no, so even why should I explore? For example, that's what I'm saying. I mean, if there is even a better value, for example, there is 200. What's the point of getting 200 for max? Because mean will not allow you to take the 200. Mean already decided I will take 2 or less. So even if you get better and better, there is no point of exploring because mean will choose less value. So already this is unnecessarily exploring the things. So what the decision? No need to explore this child, this one, and also this one, because already there is a contradiction between these two. Max is expecting greater than 3, mean is expecting less than 2, and so this is a contradiction. So this is actually the alpha beta. So this value, max value is called alpha, and the mean value is called beta. So as soon as you find any such pair that alpha is greater than beta, see 3 is greater than 2, immediately prune the other childs. So that's what we are doing, prune these things. Because alpha is greater than beta. Alpha is greater than beta means something you are looking for that is impractical, that value you will never find. And remember, we are not exploring anything. That means there is a big subtree underneath. We are pruning everything. So it's saving our time. So, well, it will continue like this, and then we'll go further, and we'll come up to this branch, the other branch, and now again it will continue like this. But should we continue here? Yes, but why? Because again, this time we are looking for greater than 3, less than 14. Yes, there some number exists because based on the max and the mean decision, max is looking for greater than 3, mean is looking for less than 14. There could have 4, there could have 5, 6, 7, 8, up to 13. Yeah, why not? We should look for that one. So that's why we should continue. And once we continue, we get another value is 5. So mean changes decision from 14 to 5. And already max has decided greater than is equal to 3. So is there any value exists between this alpha beta? Yes. Still this is there is no contradiction. It's not alpha is greater than beta. So this is not yet, this violation has not been found. So we'll continue. So yes, there exists value between 3 and 5. So we'll continue, and we can see the 2 is found. So since all the values have been found, so the decision has been changed to 2, and the max decision already 3. So already everything is done. So you can see this is exactly like the mini max with cutoff. But what is the extra advantages here? The extra advantage is with the help of alpha beta pruning, means the alpha value and the beta value, and greater than alpha is greater than beta. If we find this, then we prune this, and a big chunk of the subtree has been pruned. That is the ultimate benefit. So what might come in your exam? Um, well, I mean, this is I mean, you have to explore this one for exactly the alpha beta pruning with the tic tac toe, the same problem. So this time you can see we go up to the depth 3. So this is the depth 1, depth 2, depth 3, and now you can see in this branch a huge number of nodes has been already. We don't need to explore anything. We don't need to calculate any heuristic value, because that is already not advantageous for the max, because you can see, I mean, if you explore this one, you will understand that the decision of this one contradict with the decision of this one. Alpha is greater than beta. If you continue like this, you will understand. Right. So this is all about the alpha beta pruning. We are almost done. As you can see, alpha is greater than beta, then immediately to prune. So whatever I have explained, this is exactly the same thing with multiple simulations. You can continue like the same example, but this time not the range, with the alpha and the beta. So another way the exam questions might, you'll be given a tree like this, not the tic-tac-toe, but with a practical, with another, I mean, tree, and you can see the leaf node, and you will be asked to follow up the alpha beta pruning, and based on the alpha beta pruning, what are the nodes, what are the branches that could be pruned, and the result is this. You can see the result here. So this branch and this branch has been pruned, but you cannot write down straightforward in this way. You have to show it step by step with all the alpha and the beta values, and why those are pruned. This is very important, right? So we are done. Just one last thing, that is, we are talking about the two-player game. So it can be continued up to the 3-player, 4-player, 5-player. So for example, this particular example is for the 3-player game. Why I am showing these things? Just for one reason. This is not only 2-player. This is not only about the max and min. Sometimes there could be 3-player, 4-player, 5-player, like this. So for example, here there are 3 players game. So first move is for A, then B, then C, then A, then B, C, and it will continue like this. So for example, in the in this layer, the utility value has been given, and this is a bit different. Here the first value for A, so the first value for A, second value for B, third value for C. Again, first value for A, B, C, A, B, C, A, B, C. So these are the heuristics value for A, B, C. So like this way. Now this is the turn for A. See, this is the turn for A. So which one among these two, which one A will pick? Remember, everyone has to maximize the reward. This time there is no maximization, minimization. So everyone is trying to maximize the reward. Or chosen. So the last one, the value is 1, the value is 5, 1 and 5, 5 is bigger. So this one has been picked by the C. So now already we can see the C values. Now this is the turn for B. So what B will pick now? So this is the B. So again, we'll have to look for the B values. So here this is 2, here is 1. So again, the 2 is bigger. So this one will be picked by B. And here is 5, here is 4. Again, 5 is bigger in the context of B. So 152 will be taken. So this is the value taken by B. And now the turn for A. Now A, which one A will pick? Now see the see the beauty here. See, I mean, uh, this time for A and for A, both alternatives, A will get the reward 1. So which one A will pick? So both is same for A. One answer could be, sir, make it a random. Of course, that will work. But here A can play a game. So A can bribe B and C. Hey, I want to cooperate with B or cooperate with C. For example, in this scenario, I mean, C is in an advantageous position. C is getting, if I come to this, C will get, I mean, sorry, yeah. I mean, the reward for C is bigger than the reward for B. So maybe in this case, A will collaborate with B. So hey, C is going to win very soon. How about let's pair up? A and B will collaborate, and at this stage, maybe A will go for favoring the B. So in the real life, this is also this is something like a political game. So once you are sure that you are going to lose and someone is going to win, then you can take a party, you can collaborate with the other party, and in order to win the game, and you will play the game up to certain level with the collaboration. Then once the winning team is going to lose, then the collaboration will be broken, and then you will see, well, already C is going to lose. Now our turn, A or B. So now let's separate. There is no collaboration. Let's play with each other, and this way the collaboration uh, and the opponent things, and these are continuing one after another. The ultimate goal is to win the game. That's it. This is all about the multiplayer game, and this is done for today's class. So hopefully, yeah, I again yeah, explained a little more than I planned, but anyway, up to this slide you have to read and go for all the slides. I talked many other things that is not exactly shown in the picture, but somewhere that is written. Any question? So in short, the breadth first search, the whole tree, you can do this at the very beginning, and then we go for the backtracking, like the minimax, and then minimax with the cutoff, and then alpha beta pruning, and then the last part is the multiplayer game. These are the, you can divide into 4 segments: the normal backtracking or the breadth first search, and then the minimax, then the minimax with cutoff depth, and then the alpha beta pruning, and then the multiplayer game. So that's all for today. Thank you very much. See you inshallah on Friday.